Section 3.1 Extrema on an interval. In Chapter 3, you're gonna see so many applications of differentiation. In 3.1, we're gonna first locate the absolute extrema on an interval, and that's the first application of a differentiation. Let f be defined on an interval I containing some number c. If the y value f of c is less than or equal to all other y values for every x in that interval I, then that y value f of c is called absolute minimum of f on that interval I. That totally makes sense, right? In the interval I, for every x you plug it in for your function value, there is a y value such that it is the least among all y values, then it is called the absolute minimum. Similarly, if there is a y value f of c such that it is greater than or equal to f of x for every x in that interval I, then that y value f of c is called absolute maximum of f on that interval I. Note that a function may or may not have absolute extreme values on any given interval. You're going to actually see that example on the next page. Now, f of c is the y value. Because it's the function value, it gives the value of the actual mean or max. And c that you are plugging in is the x value, and it gives the location of a minimum or the maximum. So watch out for the problem if they're asking where the minimum or maximum occurs. Then you would give the x value where the maximum or minimum is happening. And if it is actually asking the maximum value or minimum value, then it is the y value. So you must first find the x where it's happening, and then you actually have to plug it in to find the actual max or actual minimum. So that will be the y value. So read the problem carefully, whether they're asking where it's happening or what is the max or minimum is. Determine the absolute minimum or absolute maximum or indicate that they do not exist. So if you have it, you say what it is. And if you don't have it, just say does not exist. Okay? So first problem. So we are actually assuming it starts from this value here, since there's no hole, and then it goes down, and then it goes up there. So we do have absolute max here because there is actually a value of y such that it is largest among all other y value. Yes? Yeah, that's happening at x equal 3. So absolute maximum do exist. It is 1, 2, 3. So it is y value 3. Occurs at where? It's happening when x is equal 3 as well. This is coincidence, of course. And you do have absolute minimum since this value right here is the smallest y value among all other y values. So absolute minimum will be, what is that value? -2. And where is that happening at? It's happening when x is equal 0. So it occurs at x equal 0. Next question. I mean, this graph looks all similar, but they're all different. Okay. So do we have an absolute maximum again on the second graph? Yes, you do, right? You have an absolute maximum right here. And maximum is a y value, so it is 3. Where is happening at? That is x value, so that will be at x equal 3. Absolute minimum, oops, there is a hole there where it should be the lowest point. So then be very careful. Then some people think, oh, since it's not -2, is it -1? No, because -1 value is right here. You got a whole bunch more values between -1 and -2. How many values between -2 and -1? Infinitely many. There are infinitely many y values between -1 and -2, because it could be -1.11, -1.00001, -1.999999, it could be -1.98756, and we don't even know what is the smallest y value right before -2. So absolute minimum does not exist here. Next picture. Do you have an absolute maximum? This time where it used to be absolute maximum, I have a hole there. So then I don't know what is the highest function value. It will be right below that y value 3, but you cannot say it's a 2.999999 because then someone else say, what about 2.999999999? I mean, somebody could argue all day long, right? So I do not have an absolute maximum because I cannot determine what is the highest value right below 3. So absolute maximum does not exist. What is the absolute minimum though? Do you have absolute lowest function value in this graph? Yes, it is. This is the lowest function value, which is -2. It's happening at, since it's happening right here, it's at x equal 0. Since this point right here is 0, -2. You can see that a function may or may not have the absolute extreme values on any given interval. So then, here is very valuable theorem that we're going to learn in 3.1. You must memorize, and it's called the extreme value theorem. And of course, you can abbreviate that. And even on the test, you can say by EVT. So here is what EVT says. If f is continuous on unclosed interval a to b, then f has both an absolute minimum and an absolute maximum on the interval. Well, wait a minute. Didn't you say a function may or may not have absolute extreme values on any given interval? Right. So what is this EVT is saying? It's saying if f is continuous on what kind of interval? Closed interval. So this is the first condition. First condition is f has to be continuous. Second condition has to be what's given is a closed interval, not open interval. Because if it's open interval, then as you saw right here, this is open interval, the third example. So if it's an open interval, then my endpoint is not included, and therefore if my endpoint happen to be highest value or lowest value, then you can see that absolute min or absolute max could not exist. So therefore, it is critical that we are given a closed interval. Then, if a function is continuous, meaning no holes, no jump, or no gap, and you are given on a closed interval, then that function has to have both absolute minimum and absolute maximum. If you are going to use the EVT on a problem, what is that first thing you must do? First, you gotta check to see if f is continuous. And secondly, you got to see if you have a closed interval. So let's look at the example. Determine whether the graph satisfies the EVT and identify the locations of the absolute extreme values on the interval a to b. Okay, now first you find out EVT applies. And then they said identify the locations of absolute extreme values if it exists. So they're asking where it's happening. They did not ask you actually what the absolute extreme values are. Okay, so let's do the problem. Look at the first graph. What is the first condition? Is f continuous? Yes, right? There is no hole, no jump, or no gap. So f is continuous. And then, do you have a closed interval a to b? Yes, it is a closed interval a to b. So then, does EVT applies? Yes. So therefore, your conclusion will be EVT applies. And do you have then absolute max and absolute minimum? Yes, you do. So absolute max At where? Because it's only asking you to identify the location. Which one seems higher? This is f of a, which is one of the end point, and this is one of the hill, and it's f of r. Which one seems higher to you? In my eyes, f of a seems higher. So f of a is the maximum, but since it's asking where it's happening at, it is happening at x equal a. So the location, absolute max at x equal a and absolute min at. Clearly, we can see that this is the lowest. Yeah, compared to this one. Is that right? That one's higher than f of q. So f of q is the lowest function value, so that's the absolute minimum, and it is happening at x equal q. So absolute minimum at x equal q. Now let's look at g function right next to. Is g continuous? No, there is a hole, there is jump. This g is obviously not continuous. So you just say g of x is not continuous. And because it's not continuous, what do you conclude? Extreme value theorem does not apply. When it doesn't apply, you don't talk about anything else. No conclusion can be drawn from the problem that theorem does not apply. All right, this time we are going to talk about relative extrema. Is it different than absolute extrema? Of course. If it's the same, then we wouldn't discuss about it. Absolute extrema seems absolutely it has to be the maximum value in the whole interval. And since this one says relative extrema, this relative extrema doesn't have to be absolutely the largest or absolutely the lowest. It's going to be relatively high or relatively low. That's what it's going to be. So this is actual definition of relative maximum. If there exists an open interval containing C on which f of C is the maximum, then f of C is a relative maximum of f. What is it saying? It's saying, hey, can you come up with an open interval here? So in this open interval, when you go up there, you are only looking at very little neighborhood. So you are only looking at the graph here to there. So it doesn't matter how small it is. If you can come up with an open interval such that this value is highest value in that open interval, then we're going to call it relative maximum. Therefore, every hill is going to be a relative maximum. Since around every hill, you can create an open interval so that the top of the hill is the relative maximum. Similarly, if there is an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum of f. And you can say that f has a relative minimum at C, f of C. It's the same thing like we just said. If you could come up with any open interval, let's say like right here, so that you are only looking at the graph part from here to there, so that as you see, this point right there is the lowest in that interval, then we can say that f of 5 is the relative minimum. Therefore, every value will be relative minimum. All right, let's see if we understood this correctly. Determine if f has any relative absolute extreme values. Okay, so now we have to come up with absolute max. Absolute max has to be highest function value in entire graph, okay, or given interval. But when they don't give interval and you have a graph there, then you have to look at the whole graph, all right? So you are actually looking at my whole graph from here to there and up to there. What is the highest function value? Yes, highest mark is 3. Is that right? So that's gonna be absolute maximum. Absolute maximum is a y value. So you say, yes, it is 3. What is the lowest? Absolutely lowest in entire graph. Absolutely lowest is the lowest point of this graph, which will be -1. And relative max is different story, right? You're just gonna look for every hill. And I do have a hill here. Oh, but that's absolute max. Yes. Relative max may or may not equal to the absolute max. In this case, because absolute max was a hill, your relative max will be that hill as well. But not every hill is a relative max though. Is that right? But yes, every hills are relative maximum. You could have a multiple relative max, but you could only have a one absolute maximum value. Okay, so then relative maximum is also this hill, and the maximum value is 3. And then the relative minimum is valley, so that will be this function value, which is equal to 0. Let's look at the following example. Given fx equal absolute value of x minus 1, sketch the graph and find f prime of 1. So absolute value function is piecewise defined function, correct? So we're going to rewrite it as a piecewise defined function. F of x equal x minus 1 if x minus 1 is positive. When is x minus 1 positive? If x was greater than or equal to 1. And it will come out as opposite of input if input is negative. And this input will be negative if x was less than 1. So to graph that, for all x greater than or equal to 1, I use y equal x minus 1 function. Already know it's a line, but since it's valid from 1 and more, you can plug 1 in there. It is 0. And at 2, it is 1. And at 3, it is 2. So it's a line. And then for all x less than 1, you can plug x equals 0. You get still 1. We are now plugging it into the bottom function, opposite of quantity, x minus 1. So if you plug 0 in there, you still get positive 1. If you plug negative 1 in there, you get positive 2. So you will get this part of the absolute value graph. So what is the f prime of 1 from the left? As x approaches to 1 from the left, slope of this function, or you can take the derivative of negative x minus 1 as x less than 1. That's the left derivative. The derivative of negative x plus 1 is negative 1. And what's f prime of 1 from the right? From the right, we use top function, y equal x minus 1 function. And when you take the derivative of that, I do get positive 1. So since left derivative is not equal to the right derivative, you say f prime of 1 does not exist. However, do you have relative extreme values on this graph? Yes, we do. You can make an open interval such that in this interval, this point is the lowest function value among all other y values in that open interval. So you do have a relative extreme. F has a relative minimum. And relative minimum is a y value, and that value is 0 because it says to find the relative extreme values. You give the y value. Given f of x equals sine x, sketch the graph and find f prime of pi over 2 and f prime of 3 pi over 2. So let's sketch the sine graph. Sine function, as you guys know, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is back to 0, 3 pi over 2, it is negative 1, and then at 2 pi, it's back to 0. So this is famous sine graph looks like. And I'm sure you guys all remember this. Now, what's the derivative of sine x? You know, f prime of x then is cosine of x. So what's f prime of pi over 2? That will be cosine of pi over 2. Don't look at this graph. This is a sine x. So what's cosine of pi over 2? Cosine of pi over 2 is actually 0. And do you remember what's the cosine of 3 pi over 2? Cosine of 3 pi over 2 is also 0. And you can actually look at pi over 2. The slope of this tangent line will be 0, and slope of a tangent line at x equal 3 pi over 2 will be also 0. And it says determine if f has any relative extreme values. This time you can see you have both relative maximum and relative minimum. So f has a relative maximum, and it says find the extreme values. It's not asking where it's happening, finding the extreme values, which is the y values. So relative maximum is the y value, which is 1, and a relative minimum. What's the relative minimum value? That is -1. So right before we saw f prime of 1 does not exist, and we had relative minimum there. And then this function, f has a relative maximum or minimum when their f prime was 0. So here it gives you definition of a critical number. This is extremely important. So you guys must remember this. We're going to use this after this section a lot. Let f be defined as c. If f prime of c equals 0 or f prime of c does not exist, then c is a critical number of f. So a lot of time you guys only remember like this and it gives you a problem. You also gotta remember this one. Because f prime of c equals 0, then f of c exists for sure. So the problem occurs when f of c does not exist and f prime of c does not exist also, and you think that's a critical number. That's not the case. If f prime of c does not exist and f of c does not exist either, then c is not a critical number. Okay? For f prime of c does not exist, and in order for c to be a critical number, f of c has to be defined. F of c has to exist. Okay? This is, I think, easier to remember. If f prime of c equals 0 or f of c exists, but f prime of c does not exist, then c is a critical number of f. Do you actually understand the critical number now? Okay, so if f prime of c equals 0, then c is a critical number. Also, f c exists, but f prime of c does not exist, then c is a critical number of f. Okay, fine. What about critical numbers? This is why critical number is so important. The next theorem says if f has a relative minimum or relative maximum at c, then c is a critical number of f. What is it saying? If you have a relative max or min, it's only happening at a critical number. That's what it's saying. But converse is not true. What's the converse of a statement? That's switching if-then clause. So if you say, oh, if c is a critical number, then f of c is a relative max or relative min. No, that is not true. So just because c is a critical number doesn't guarantee that you will have a maximum or minimum there. But if a relative maximum does exist, then it's only happening at a critical number. That's what it's saying. So make sure that it is clear. Okay? So for example, look at it. The first example. You have a relative minimum here. And what is the f prime there? F prime of 5 is 0. Is that right? And you have right now relative maximum here. And what is the f prime there? F prime of 3, it's a sharp turn, so does not exist. But is f of 3 exist? Yeah, f of 3 has to exist, because if f of 3 does not exist, we cannot call that a maximum, right? Because you don't have a maximum value then. So that's why this is critical, that f of 3 has to exist, and only f of prime 3 does not exist. So that it's still, sharp turn still could give you a relative maximum there. Does that make sense? But not every critical point will have a relative extrema, because if you look at the first example, if my graph looks like that, you can see f prime of 7 is 0. I have a f prime of 7 equals 0, but I don't have a relative max or relative minimum there, because my graph goes down this way and it is going up this way. I cannot find any open interval so that this is the highest or this is the smallest. Now, h of 2 exists, right? It's right here. However, h prime of 2 does not exist. How come? Well, this function h, there is a jump discontinuity at x equal 2. And therefore, it is not continuous at x equal 2. And when the function is not continuous at a point, it is not differentiable at that point. So therefore, h prime of 2 does not exist. So 2 is a critical number since h of 2 exists, but h prime of 2 does not exist. So 2 is a critical number, but I don't have any relative extrema there. So know that this theorem only goes to one direction. Method for finding absolute extrema on a closed interval. Consider a continuous function f on a closed interval a to b. So this method, of course, works if EVT applies. So this should be actually first step for you when somebody says to locate the absolute extrema. Because if your function is not continuous, or if interval given is not a closed interval, then we cannot guarantee that absolute extrema exists. So therefore, we cannot use this method. So actually, first step should have been to check for continuous function on a closed interval. And if you do have a continuous function and what's given is a closed interval, then you can say by EVT, extreme value theorem, absolute extrema exist. And then now you can do the second step here, find the critical numbers of f, because all relative maximum and relative minimum happens on a critical number. So you're going to find all critical numbers and evaluate their function values at each critical number. Because you saw earlier, I could have a graph like that. So although even if you have relative maximum, I could have absolute maximum happening at the end point. So you're also going to evaluate end points. So that will be step 4. And among all the function value of each critical numbers and including endpoint, you are going to call the smallest y value absolute minimum and the largest y value absolute maximum. Make sense? So let's go ahead and do a few examples now. Find the absolute extreme values of f of x equal x to the 4th minus 2x cubed on closed interval negative 2 to 4. Step 1, since f is continuous on R, because it's a polynomial, it is continuous on this closed interval negative 2 to 4, and you already put the closed interval there, thus EVT applies. So now I'm going to find the critical numbers. To find the critical numbers, you have to find the f prime of x and set it equal to 0, or find out when this is going to be undefined or does not exist. So f prime of x is 4x to the 3rd minus 6x squared, and this is never undefined. This exists for every x. So only way you can get critical number is if this was equal to 0. So set it equal to 0, I can factor out common factor 2x squared. Then I have a 2x minus 3 equals 0. So first critical number, you get it from here, is this happens when x equals 0 or this happens when x is equal 3 over 2. So you found the two critical numbers. So step 3, you're gonna evaluate f of 0 and f of 3 over 2 because any relative minimum or relative maximum occurs on a critical number. So f of 0 is 0 to the 4th minus 2 times 0 to the 3rd, which is 0. F of 3 over 2 is 3 over 2 to the 4th power minus 2 times 3 over 2 to the 3rd power, which is 81 over 16 minus 2 times 27 over 8. So then that's equal to 81 over 16 minus 54 over 8. I'm gonna get a common denominator, so actually I can subtract them. And the common denominator is 16. 81 minus 108. That will be negative 27 over 16. But absolute max or absolute min could happen at the endpoints. So I'm going to evaluate endpoints. So what's f of negative 2 now? So negative 2 to the power 4 minus 2 times negative 2 to the 3rd power is positive 16 plus 16, which is 32. F of 4 is 4 to the power 4 minus 2 times 4 to the power 3. That is 4 to the 4th is 256 minus 4 cubed is 64. 64 times 2 is 128. And 128 is half of 256. So when you subtract that, you're going to get another 128. So among these four values, pick the largest value. What's the largest value do you see? Largest value is this one, 128. So this is your absolute max. What is the smallest value? Smallest value is this one, negative 27 over 16. So that will be absolute minimum. So absolute maximum happened at the end point, and your absolute minimum is actually the valley. So let's conclude. So now step 5, you have absolute max 128 at x equal 4 and absolute minimum negative 27 over 16 at x equal 3 over 2. Let's do a couple more examples. Find the absolute extreme values of f of x equal 2x over quantity x squared plus 1 on closed interval negative 2 to 2. Okay, so step 1, you can see how this function is a rational function. A rational function is continuous in their domain. However, because your denominator is never 0, because x squared is greater than or equal to 0, that makes x squared plus 1 always greater than or equal to 1, which means x squared plus 1 is never equal to 0. So f is continuous on R, thus f is continuous on closed interval negative 2 to 2, hence EBT applies. Step 2, I'm going to take the derivative and find the critical numbers of f. So let's go ahead and take the derivative. F prime of x equal, since this is a rational function, we're going to have to use a quotient rule. So low d high minus high d low over square below. Then I will get 2x squared plus 2 minus 4x squared over x squared plus 1 squared, which is equal to then negative 2x squared plus 2 over x squared plus 1 squared. So then you can factor out negative 2 on the top. I get x squared minus 1 over x squared plus 1 squared. But x squared minus 1 in the parentheses factors more. So you're gonna factor completely and write x plus 1 times x minus 1 over x squared plus 1 squared. And you found your derivative. So now I gotta find the critical numbers, and critical number is an x value such that your f prime is 0. My f prime is a fraction right now. When is fraction 0? Fraction is 0 when numerator is 0. So this f prime will be 0 if x was 1 or -1, right? F prime equals 0 when x equal plus minus 1. And when is this f prime does not exist? Well, this f prime always exists because for any x you plug it in there, your denominator never can be equal to 0. So you only have two critical numbers, and it is x equal plus minus 1. Okay, step 3, you have to evaluate function value at critical numbers. So first, my critical number is 1, so let's calculate f of 1. F of 1 is 2 times 1 over 1 squared plus 1, which is 2 over 2, which is 1. F of -1, which is my another critical number, is 2 times -1 over -1 squared plus 1, which is -2 over 2. So it gives me -1 function value. Number 4 step, I need to evaluate function value at each endpoint. So let's find f of -2, and that is 2 times -2 over -2 squared plus 1. That's a -4 over 4 plus 1 is 5. That's a -4 fifth. And then I had another endpoint, which was 2, and f of 2 is 2 times 2 over 2 squared plus 1. That is positive 4/5. Now I have to determine what's my absolute max and absolute min. So out of 4 values listed in step 3 and 4, look for the highest value. What is the highest function value? Is 1 bigger or 4/5 bigger? 1 bigger. So this is your absolute max. And what is the absolute min? Which one is lower, -1 or -4/5? It is -1. So your absolute minimum is going to be the -1. And they actually both happened at a critical numbers. Our endpoints didn't count for absolute max or absolute min this time. So let's now make a conclusion. You have absolute max. What's the absolute maximum value? 1 at x equal 1. And you also have absolute min, and it is -1 at x equal -1. Okay guys, this is the last question for the section 3.1. Find the absolute extreme value of f of x equal x minus 3x to the 2/3 power on -8 to 64. This function it's x minus 3 times cube root of x squared. And cube root of a function is defined on all real numbers, and it is continuous on all real numbers. Because f is continuous on all real numbers, it will be continuous on -8 to 64. You can just state that, okay? So step 1, since f is continuous on R, it is continuous on -8 to 64. Thus, EBT applies. Step 2. Now you're gonna find the critical numbers, and to find the critical numbers, I need to find the derivative. So then, what's the derivative of x? That's 1 minus 3 times, what's the derivative of x to the 2/3 power? We move the power down to the front, and we lose 1 power, and 2/3 minus 1 is -1/3. So then we can cancel the 3's, and I can rewrite this with no negative exponent, and it will give me 2 over cube root of x. Yeah, and if you want to use common denominator, 1 is a cube root of x over cube root of x. So I can actually write as a cube root of x minus 2 over cube root of x. Why do you do that? Well, you gotta write like this to see when f prime is 0 or when f prime does not exist. Okay, so you can see this derivative is equal to 0 when is f prime 0? If a cube root of x on the top was 2, 2 subtract 2 will give you 0. And cube root of who is equal to 2? That will be 8. So x equal 8 is a critical number because cube root of 8 is 2. 2 subtract 2 is 0. And numerator will be 0 and denominator isn't. So therefore, your f prime will be 0 at x equal 8. Also, we just said f is continuous on R, meaning it is defined on all real numbers. However, you can see now f prime does not exist at x equals 0. This f prime does not exist when x equals 0, but f of 0 exists. So it is also critical numbers. So I have 2 critical numbers this time as well. And step 3, we are going to evaluate at each of these critical numbers. So f of 0 is equal to 0 minus 3 times the cube root of 0 squared, which is 0 minus 0, so it is 0. And f of 8 is 8 minus 3 times cube root of 8 squared, which is equal to 8 minus 3 times cube root of 64, which is equal to 8 minus 3 times 4 is 12. So you get negative 4. Now I'm going to evaluate function value at each of the endpoints. And f of negative 8 is negative 8 minus 3 times the cube root of negative 8 squared, which is negative 8 minus 3 times the cube root of 64, which is equal to negative 8 minus 3 times 4 is 12, so you get negative 20. F of the other endpoint 64 is 64 minus 3 times cube root of 64 squared, which is equal to 64 minus 3 times. I'm just gonna think this is a cube root of 64 times 64 because it's a 64 square. And each of the 64 will come out as 4, so that will be 4 times 4, which is equal to 64 minus 16 times 3 is 48. And when you subtract 64 minus 48, you get 16. All right, so step 5. I need to make a conclusion out of all these 4 values. What is the largest value? I see largest value is right here, 16. And what is the smallest value? Smallest value is negative 20. So this time my absolute max and absolute minimum both happen at the endpoint. So this function, absolute maximum is 16 and it is happening at x equals 64, and absolute min, which is negative 20 at x equal negative 8. Alright, this is everything about section 3.1. Please study, don't get behind, and I will see you in section 3.2.